Hello, my name is George, and I'm here today to talk to you about an important element called boron. If we look at the picture to the right, we see the big letter B, and that is boron symbol. Boron symbol is B. If we look up from boron symbol, we see the number 5. 5 is boron's atomic number. It represents the fact that boron has 5 protons. If we look down from boron symbol, we see the number 10.811, and that is boron's average atomic mass. Now let's look at some physical properties of boron. Boron's melting point is at 2349 Kelvin, which is around 2000 degrees Celsius. Its boiling point is at 4200 Kelvin, which is around 4000 degrees Celsius. Its density at 20 degrees Celsius, which is around room temperature, is 2.34 grams per cubic centimeter. If we look at the picture to the right, we can see that boron's color is black-brown. Notice that boron is a metalloid. What does a metalloid mean? A metalloid means that this element has 2 of the 3 properties of a metal. So what are the 3 properties of metal? Metals have luster, they conduct electricity, and metals are malleable. So which one does boron not have? Boron is not malleable. Boron is brittle, and that is why it is a metalloid, not a metal. Boron is also a semiconductor. What is a semiconductor? A semiconductor is a solid substance that has the electric conductivity between that of an insulator and that of a conductor. These semiconductors are essential components of most electronic circuits. So basically, a semiconductor conducts electricity, but doesn't have as well as a conductivity as a conductor. Now let's look at some chemical properties of boron. At room temperature, boron does not react with oxygen. At higher temperature, however, boron reacts with oxygen and forms boron trioxide. Boron does not react with hydrochloric acid, HCl. Boron does not react with hydrofluoric acid, HF. Boron reacts with nitric acid, HNO3. Concentrated nitric acid is able to slowly oxidize powdered boron. And now we see the word oxidize. What does that mean? Oxidize is the verb for oxidation. Oxidation is a process in chemistry where a molecule or an atom loses electrons. So what this is saying here is when you put powdered boron into concentrated nitric acid, boron loses electrons. And that's how they react. On the left of the picture, in this picture, you can see a model of boron's atom. There are 5 protons, 1, 2, 3, 4, 5, and there are 6 neutrons. 5 protons, 6 neutrons. That will be 11. So the atomic mass of this atom specifically will be 11. However, we're seeing on the first slide that the atomic mass, the average atomic mass of boron is not that close to 11, it's 10.8. And that is because this atom only models one of the isotopes of boron. We'll see the other one on the next slide. So as I've mentioned, boron 11 has 6 neutrons. As we've seen on the previous slides, boron 11 and boron 10 are both isotopes of boron. Since we mentioned that boron has 5 protons, then boron 10 must have 5 neutrons. Number of neutrons is what differentiates between these 2 isotopes. Boron 10 has the abundance of about 19.9%. Boron 11 has the abundance of about 80.1%. These 2 isotopes are all stable and naturally occurring isotopes of boron. Each of these isotopes has important applications in our society and in many industries, and I'll go on to talk about this later on in this presentation. So now let's look at the history revolving around boron and how this element was discovered. So in the pictures on the left, you can see two French chemists, Joseph Louis Gay Lussac and Louis Jacques Denat. Don't mind my bad French. These two French chemists discovered boron on June 30th, 1808. However, a British chemist, Sir Humphrey Davy, also discovered boron on the same year. These chemists, the French chemists and our Sir Humphrey Davy, independently discovered boron. They're all discoverers of this element. However, they discovered boron, they isolated boron in different ways. The French chemists used iron to reduce boric acid at high temperature, and then they were able to confirm the existence of boron. Now we see another word called reduce here. Reduce stands for reduction. It's the opposite of oxidation. Reduction is a process in chemistry where a molecule or an atom gain electrons. So now when I say these French chemists use iron to reduce boric acid, meaning that boric acid gained electrons. Our British chemist, Sir Humphrey Davy, used a different method. He first attempted to send electric currents through a solution of borate, and then noticed the formation of a brown precipitate. He then used potassium, not iron, to reduce boric acid. And then he was able to produce enough boron to confirm a new element. He named the element at first to be boracium. This name was later on changed to be boron. Now that we've talked about the history and the properties of boron, you might be wondering, how does this element interact with humans? Where is this found? So now let's talk about where boron is found. Elemental boron, boron atoms that are not attached to any compounds, is not naturally found on Earth. These boron atoms are found in small amounts in meteoroids. Boron as an element itself has a really low abundance in the solar system and in the Earth's crust. Boron is concentrated on Earth and forms of naturally occurring boron compounds, the borate minerals. The borate minerals, the most prominent borate minerals include borax and kernite. Borax is sodium borate. Kernite is hydrated sodium borate hydroxide. These are both minerals, really important minerals. In the picture on the side here, we're showing a picture of borax crystals. The largest proven boron deposit, when I say boron deposit, it means borate minerals deposit, is in Turkey. So now we've seen that boron on Earth is mostly attached to and compounds with other elements. How do you get elemental boron? How do you get pure boron? In chemistry labs, we're able to get pure boron by reducing volatile boron halides with hydrogen. Boron halides are molecules that consist of boron and a halogen. Now we all see the word reduction. As I mentioned, reduction means the process of gaining an electron. So now in this process, these boron halides gain electrons from the hydrogen. So what are halogens? What are halogens that are involved in this boron halide compounds? Halogen is not an element. Halogen is a type of element, which includes fluorine, chlorine, bromium, iodine, and astatine. So boron halide is a molecule that consists of one of these elements and boron. Boron is also important in biology. Boron plays a strengthening role in the cell walls of all plants. The pictures on the left is showing an experiment testing for boron deficiency. Boron deficiency is the deficiency of micronutrient boron. And the experiment pictures, you can see that the control group is doing totally fine, and there is boron in the plant. In the other groups, there's the absence of boron. And in the last picture, we can obviously see yellow stuff forming on the leaves, which indicates boron deficiency. Boron deficiency can cause large losses in crop production and crop quality, which proves the fact that boron plays a crucial role in cell walls of plants. Experiments by biologists has also shown that boron may be an ultra-trace element and may have an important role in animals as well. Borates have a low toxicity in mammals, but it is more toxic to arthropods, and borates are used as pesticides. Boron is mildly antimicrobial, and there is a natural boron antibiotic that was discovered by the scientists. In the picture on the right-hand side, it is showing NASA's Orion spacecraft, the Mars Transfer Vehicle. And these spacecrafts may be used in the future in humans' mission to Mars. So why am I showing you this picture? I'm showing you this picture because it deeply relates to the application of boron. When these spacecrafts travel through the vastness of space to another planet, they have to be able to undertake large amount of cosmic rays. Cosmic rays. Cosmic rays are high energy protons. When these cosmic rays hit the surface of the spacecraft, they cause secondary radiation, and this is not good for the spacecraft itself and the crew within the spacecraft. Boron-10 can be potentially used as a structural material for future interplanetary spacecraft because it is effective in dealing with both cosmic rays and secondary radiation. It will be used on spacecrafts in forms of boron fiber, which is a really strong material. Boron can provide the mechanical reinforcement and radiation protection for the spacecraft. On a side note, boron-10 is also used in nuclear reactors for reactivity control and in emergency shutdown systems. Interestingly enough, boron-11 is also related to our deep space exploration in the future. Boron-11 is largely immune to radiation damage, and this is really useful, and I'll explain why. The cosmic radiations and the secondary radiation may irritate the semiconductor chip structures, which is really important for the computers on board the spacecraft. These radiations may potentially lead to data loss, which is not good for a long-term space mission. So we must design radiation-hardened semiconductors. What material should we use for these semiconductors? As I've said, boron-11 is largely immune to radiation damage, and that is why it is a perfect material for radiation-hardened semiconductors on these spacecrafts. And that is how boron can help humans with our future space missions. There's also other applications of boron, more common ones. For example, boron fiber. As I've said, boron fiber is a high-strength, lightweight material used primarily for the aerospace industry, but there's also limited production for consumer products and sporting goods, such as golf clubs and fishing rods, which use boron fiber. On the picture on the left-hand side, you can see that boron fiber is being used in this fishing rod. And the fishing company said because it's what's inside that counts, and that is saying boron fiber is a really strong material and it makes really good fishing rods. Another important application of boron is boron fiberglass. Fiberglass is a fiber reinforced polymer made of plastic reinforced by glass fibers. Boron is added into these fiberglass to increase the strength of the glass. Boron is added in forms of borosilicate, borax, or boron oxide. Boron-containing fiberglass actually consume half of the global production of boron because it is so commonly used around the world in construction and insulation. On the left-hand side, you can see a picture of boron carbide ceramic. Boron carbide ceramic with the chemical formula of B4C, is material with extreme hardness and toughness. It is used in tank armor, bulletproof vests, and many more structural applications and materials. On the right hand side, you can see a picture, a really interesting picture. You can see silicon here, you can see boron here. So what is this picture? This picture is an exaggerated representation of the inside of a semiconductor. And what does boron do in a semiconductor? Boron is an excellent dopant in a semiconductor. So what is a dopant? A dopant is a trace impurity element inserted into a substance to alter the substance's electric or optical properties. So in these semiconductors, including silicon, germanium, and silicon carbide semiconductors, boron can help these semiconductors to have the necessary electric conductivity in order for them to produce transistors and diodes, which are really important in the computer industry. So I have talked to you about the properties of boron, the history and discovery of boron, and how boron interact with the natural world and how it interact with humans, and also many of the applications of boron in the aerospace industry and many more. Boron is indeed a really important element in our world. And thank you for your time. Thank you for listening to my presentation. Goodbye.